So good evening. I thank the organizers for giving me an opportunity to have a talk in this conference. I really like the idea of mixing people from different fields. And I am a stranger here. So I'm trying to, even though I'm trying to, the subject discussed here is too difficult for me, but I'm trying to get the idea of what's going on in this interesting field. And I'm from Kyoto University, Division of Chemistry, working on solid-state NMR. And in our NMR room, we have several superconducting magnets as well as home-built magnet and a permanent magnet. And each magnet is equipped with a number of probes, a kind of LC circuit for different purposes, as well as RF components and an NMR spectrometer. Matter is made of an atom, and each atom has atomic nuclei, which can have spin depending on the isotope of your interest. And the dynamics of this spin depends on the externally applied field as well as the intrinsic local field produced by the chemical environment. That's why we can do something about chemistry using NMR. That is, NMR signal, or its Fourier transformed version of NMR spectrum, is determined by the local field produced by a kind of spin Hamiltonian, like chemical shielding interaction, dipolar interaction, and quarter-polar interaction, and so on, through the Liouville von Neumann equation. And usually, these internal interactions affect in a complicated way to the NMR spectrum. And that's why we apply such RF irradiation with different various modulation in order to manipulate the nuclear spin Hamiltonian. So that's what we do. It's something like music composition. So we design the sequence of RF pulses applied to nuclear spin system, thinking about the structure or what kind of information you want to extract. And this is just an example. We have unlimited number of variation in the way that we apply RF pulses. And we can apply it to various chemical systems. This is just an example. For example, we studied amyloid beta protein, which is responsible for Alzheimer's disease. It is a bit complicated protein composed of 42 amino acids. And if it aggregates in your brain, it causes Alzheimer's disease. And interestingly, it is known to interact with curcumin, a kind of curry spice. It doesn't mean you are free from Alzheimer's disease if you eat curry too much. Don't try to do that. But it is known curcumin has something to do with preventing Alzheimer's disease. That's why we are interested in how these curcumin molecules interact with the amyloid beta protein. And this example shows a carbon-13 NMR spectrum of a mixture of amyloid beta and curcumin. So in chemistry, we have a complicated structure originating from what we call chemical shielding effect. And we designed such pulse sequences that tells us which carbon site is in spatial proximity to which amino acid residue and so on. This is an example. And from this two-dimensional NMR spectrum, we can tell something about the structure of this complex molecule. Another example. The sample is a bit simple, a glycine, a kind of an amino acid. And this is a usual solid-state NMR spectrum of carbon-13. And if we irradiate RF pulses at the nitrogen in the vicinity of this carbon, we got this structural spectrum, and we compared a numerical simulated spectrum, assuming that the internuclear distance is 1.5 angstrom, which perfectly matches with the experimental one. So we could tell that interatomic distance between this carbon and nitrogen was 1.5 angstroms. So in this way, we can design pulse sequence like music composition on a synthesizer, music synthesizer. And for this purpose, commercial NMR spectrometer is available. I have to say they are so sophisticated and useful. But in my personal opinion, they are too sophisticated. You cannot hope to hack the system. That's why some time ago, I started a project of open resource NMR spectrometer alone. And this is called the OPENCORE NMR project. And there are information available on this website where you can get board design, free software, and so on. But I have really a long history about this development together with a mountain of garbage boards. But I skip all this long, interesting story. I just say, in the end, I did make something that works. And I decided specification so that I want to use it as it is. So it has 3 RF channels, and RF frequency is up to 600 megahertz, simply because we happen to have 14 Tesla superconducting magnet corresponding to proton resonance of 600 megahertz, and so on. And in our laboratory, all of our NMR systems are equipped with this home-built OPENCORE NMR system. And we are using this spectrometer for various chemical analysis, including organic material, inorganic material, battery material, and so on. And we are also interested in the dynamics of spin. In this example, we were curious what would happen if you rotate nuclear spin simultaneously along 2 different axes. The corresponding time evolution operator is rather simple, but the corresponding Hamiltonian is very complicated. You need to apply very complicated amplitude and phase modulation, but we could program it on our system. And the spectrometer happened to be so small that we can bring the spectrometer out of our laboratory. Once upon a time, I was asked by Kyoto University Hospital to measure the field stability of the MRI system in the hospital. So I brought my spectrometer in the MRI diagnosis room and made a quick measurement. I had to do it quickly because a patient was waiting outside. And I got a 1 Tesla permanent magnet, which is portable. So I could demonstrate the real-time NMR in a classroom in front of undergraduate students who were blankly looking at the screen. But it was unfortunate I can't do it right now. It's very difficult to bring this magnet on an airplane. And once upon a time, I also brought my whole NMR portable system to my home just to play with NMR at my home. And another project I'm involved in was MRI built from scratch, including superconducting magnet, gradient coil, and RF coil, and so on. In this project, I myself was responsible for providing the spectrometer and modifying it for MRI purposes, making measurements and data processing and make images. So At first, the image was terrible, but finally, we got something very nice. And note that my dear baby was not the sample. Instead, we measured monkey brain. We brought it from somebody else. And we could also perform or pack the whole NMR system on a bookshelf in our office to measure NMR as well as MRI. And extension to X-band microwave was straightforward to perform ESR measurement. So this is a brief introduction to what we do and who I am. In short, we hack NMR system in order to hack nuclear spin dynamics. But in our NMR community, we are suffering from the problem. The only problem is the sensitivity. So in our community, great efforts have been paid to improve sensitivity, including nuclear hyperpolarization, development of ultra-high field, and development of very cold detection circuit, and so on. And we came across a paper published by a group led by the previous speaker of this session, where they demonstrated RF to light up conversion using silicon nitride membrane. I was deeply impressed by this paper. And as soon as I have read this paper, I got interested in applying this idea to NMR. So that's the beginning of this story. Very naive and oversimplified cartoon is put here. We have an LC circuit composed of an inductor and a membrane capacitor. And inside an inductor, we put chemical compounds containing a lot of nuclear spins inside. Then we can expect the electromotive force due to nuclear induction shakes the membrane, and then displacement can be read out by an optical means. So we call this project as Electro-mechano-optical, or EMO NMR. And at first, I didn't know where to begin, what to do. But very fortunately, I could collaborate with very amazingly talented people, including one of the organizers of this conference, Usami-san. So we began development of the membrane capacitor using the commercially available membrane. So in this conference, I don't have to explain a bit this to detail. And we use vacuum deposition, and in a clean environment, we assembled metal-coated membrane into a capacitor. And we placed it in a vacuum chamber to avoid air friction, and made an optical cavity inside a vacuum chamber using the ring piezoelectric device. And the capacitor electrode is connected on the wall through to the outside through a hermetically sealed SMA connector. And for the optical detection, we employed differential detection for technical reasons. And we managed to detect thermal membrane oscillation. Here shows an optical detected membrane thermal spectrum. Here we see fundamental 1-1 drum mode and 1-2 and 2-1 and higher oscillation modes. And we use this fundamental mode. And for NMR demonstrations, we employed that permanent magnet. Once upon a time, we brought, or I have brought it to my home to play with NMR. So, and the target materials for the time being was just water, and the proton resonance was about 43 megahertz. So the membrane frequency was on the order of 100 kilohertz, while the LC or NMR frequency was 40 megahertz. And that's why we needed a drive signal frequency corresponding to either the sum or difference of these frequencies. So based on this, we fabricate something like this. We have a pair of crossed coil. Photo is put here. One is a solenoid coil, and the other is a saddle coil. And saddle coil is used just for exciting nuclear spins. And the solenoid coil is connected to the membrane capacitor in parallel. And to adjust the resonance frequency, we put an additional trimmer capacitor here. And for drive signal irradiation, we built a sort of balanced circuit, and the drive signal was differentially applied to this LC circuit. So we expect the nuclear induction signal shakes this membrane inside a vacuum chamber, and this membrane oscillation would be detected by an optical photodetector. And by the way, the Q factor of this LC circuit was about as low as 20. And this is an overview of our EMO-NMO system. And on the optical bed, a number of optical components are put, so the picture is a bit complicated, but we have a vacuum chamber here, and 1 Tesla permanent magnet here, and RF component like trimmer capacitor and so on. And after some trial and error, we managed to detect something that convinced us it was an NMO signal detected by the optical means. So we celebrate, it was 2016, so we celebrated the birth of EMO-NMR together with 70th birthday of NMO in condensed matter. And we needed to analyze the sensitivity or signal to noise ratio. For this purpose, we thought of a model composed of a chain of harmonic oscillator of LC and membrane and optical cavity with an input and an output. And the effective Hamiltonian looks like this. And starting from this Hamiltonian, after some or great algebra calculation, we estimated the single shot signal to noise ratio of this experiment. I skipped the detailed calculation. Detail is discussed in this paper, but the result was on the order of 0.1, which is not good at all. But it roughly explained what we observed. And we found that this term, that is the drive phase noise, contributed a lot to the overall sensitivity in a bad direction. In order to induce electromechanical coupling, we need to apply the drive signal in a parametric manner. And as you increase the power of this drive signal, we observe that the optically detected membrane spectrum, its noise floor increased with the drive power. So we needed to do something, and came to one idea, a simple idea, to change the material of the metal coating on the membrane from gold to aluminum. Even though the light reflectivity is lower for aluminum, but it's significantly lighter compared to gold layer. So we observed that the membrane fundamental oscillation frequency increased from 180 to 430 kilohertz. This is just a tiny improvement, but its effect on the phase noise was drastic, we found. This is, again, membrane spectrum. And as we increase the drive power to the maximum available power that we can do it, and we did not observe any increase in the flow of the noise level. So under this condition, we did the same experiments again. And this shows a conventionally electrically detected NMR signal. And using the same sample, we observed optically up-converted EMO signal here. And the bottom spectrum shows their Fourier transformed signal. And in a conventional electrical signal, the origin of the line width is just due to the inhomogeneity of our permanent magnet. While for the membrane its bandwidth is very narrow, so we can only see a fraction of the spectrum. But the sensitivity was significantly improvement. And honestly, I have to say, there is still much room for improvement. So we decided to continue our research along this line. And in progress, we need to increase the electromechanical coupling. So one straightforward way is to increase the Q factor of the circuit, LC circuit. And our collaborator is very good at manipulating high temperature superconducting material, and they designed spiral shape on a substrate to make a self-resonating structure at 40 megahertz. And at 20 Kelvin, the Q factor of this self-resonance was about 9,000. And for a frequency as low as 40 megahertz, this Q factor is very, very high, I have to say. So next step will be to combine our optomechanical system with this, using this HTS coil. And we are also interested in exploring the physics of spin cavity coupling using not electrospin, but nuclear spins. So this could be used, I hope, together with nuclear hyperpolarization technique. And along this line, we got interested in performing spin cavity coupling. So honestly, this is nothing new. We just reproduced the paper reported here, but we wanted to reproduce it. So using a dielectric resonator, the radical DPPH sample was packed tightly in this hole. And then the dielectric resonator was put inside our partially 3D printed electromagnet, and then connected to a network analyzer and observed S11 parameter for various magnetic field strengths. So as we expected, as the resonance of electron spin approaches to that of the dielectric resonator, we saw some like this. This is, I think, called vacuum Rabi splitting. I'm not familiar with this field, but I'm trying to study hard what's going on here. So next step will be to demonstrate this splitting using nuclear spins. Of course, the gyromagnetic ratio of nuclear spins are orders magnitude lower than the electron spins, so I realize it's challenging, but I try to do it. And in progress project is just to combine the MRI system, its detection, with the optomechanical system. So for this purpose, we began to develop field gradient coil. This is a film. And on both sides, these exotic patterns are printed. And if you roll this film into cylindrical shape, then you can have a field gradient coil. It has three channels where you can apply field gradient along Z and X and Y direction so that you can encode nuclear spin state depending on the position inside this field gradient coil. Hopefully, we will be able to get image like this using the optomechanical device in the future. This is the end of my talk, and thank you for your attention.